Positioned 1 mile off England's most westerly coordinate, Longships Lighthouse operates as a critical maritime watchtower guarding the strategic approaches to the Celtic Sea. The original facility, commissioned in the late 18th century, proved structurally inadequate against the kinetic force of the Atlantic Ocean at 12 meters high. Heavy swells routinely obscured the primary beacon, compromising the navigational safety of the surrounding maritime choke point and demanding a rapid infrastructural escalation. In 1873, engineers deployed a heavily fortified granite tower, elevating the operational focal plane to 35 meters to guarantee uninterrupted signal transmission. Despite this significant vertical advantage, extreme weather systems continue to project rogue waves directly over the reinforced lantern room during peak atmospheric disturbances. The integration of a structural helipad in 1974 fundamentally altered the logistical profile, establishing a vital aerial bridgehead for rapid personnel deployment. This modification eliminated the hazardous maritime transfer protocols, allowing maintenance crews to bypass hostile sea states and access the primary installation directly. By 1988, technological advancements permitted full automation of the facility, triggering the systematic withdrawal of the permanent forward operating personnel. Following this shift, Longships transitioned to a remote telemetry architecture, transmitting real-time diagnostic data to regional command centers for continuous systemic oversight. Currently, all active automated outposts are strictly monitored 24 hours a day from the centralized Trinity House operational headquarters located in Harwich. The present tactical deployment represents the second phase of a biannual maintenance schedule designed to ensure total operational readiness of the lighthouse. A comprehensive structural and systemic audit conducted 6 months prior generated the specific technical mandate for this current specialized intervention team. Assigned objectives range from minor mechanical calibrations on security infrastructure to realigning sensitive electronic guidance components back into optimal specification ranges. In severe cases, the physical maintenance profile involves hazardous and rudimentary manual interventions, such as extracting biological blockages from the internal waste macerator. A primary objective for this rotation involves overhauling the localized fire suppression grid housed within the lower-level electrical generation compartment. The legacy pyrogen canisters, acting as the primary defense against internal combustion events, have reached the end of their certified operational lifespan. Technicians must systematically detach the expired suppression units before integrating the newly requisitioned aerosol generator components into the central defensive grid. Once the obsolete hardware is successfully extracted, the team initiates the complex rewiring protocol to bridge the new canisters into the control matrix. With the explosive charges isolated, technicians execute a simulated ignition event, applying thermal anomalies to dual sensors to verify the activation logic. The successful illumination of the primary control panel confirms that the pyrogen deployment sequence functions perfectly under simulated catastrophic failure parameters. Following the primary system check, engineers reset the automated response matrix and manually test the emergency abort sequence to ensure human override capabilities. Sustaining peak physical and psychological efficiency requires careful nutritional management, leading personnel to prefabricate rations prior to deployment on the isolated station. The rigid spatial constraints of the internal galley require rapid and efficient meal preparation, minimizing energy expenditure during high-intensity maintenance cycles. Off-duty recovery protocols involve basic psychological decompression in the reinforced sleeping quarters, utilizing digital entertainment and literature to mitigate operational isolation. By the second operational cycle, the installation prepares to receive essential logistical reinforcements, primarily focusing on raw hydrological and hydrocarbon resupply. A persistent strategic query concerns the methodology of sustaining potable water reserves in a highly saline environment devoid of natural catchment potential. Utilizing external rain catchment systems is tactically unviable, as the exterior structure is constantly contaminated by avian biological waste and marine detritus. Desalination technology, utilizing reverse osmosis, was systematically evaluated, but ultimately rejected due to the severe imbalance between maintenance costs and actual consumption rates. Current infrastructure relies on hardened internal storage reservoirs, presenting a zero-maintenance logistical solution that vastly outperforms complex filtration machinery in hostile sectors. Aerial transport delivers flexible bladders containing 400 liters of potable water directly to the reinforced landing zone situated above the lantern room. Personnel immediately establish a hardline connection between the external bladders and the internal gravity-fed transfer system to secure the vulnerable liquid assets. The transferred fluid descends through the core of the masonry structure, accumulating in a heavily shielded containment vessel located at the base. Prior to human consumption, the stored water is forced through a strict filtration matrix and ultraviolet sterilization array to neutralize any biological anomalies. Routine operational audits mandate rigorous chemical testing of the water supply, ensuring the hydration reserves meet precise safety parameters for deployed personnel. Upon completion of the fluid transfer, the exhausted transport bladders are secured within a tactical cargo net for immediate aerial extraction. The extraction aircraft departs the airspace, completely severing the logistical tether and leaving the maintenance squad isolated for the next 10 days. Shortly after securing the perimeter, Command transmits high-priority atmospheric alerts, indicating a severe meteorological disturbance advancing directly toward their geographic coordinates. Radar telemetry confirms the approach of Storm Goretti, projecting a massive low-pressure system designed to test the absolute limits of the structure. Predictive models calculate sustained aerial velocities exceeding 60 miles per hour, with potential rogue gusts peaking at 90 miles per hour. The initial phase of the anomaly presents a deceptive calm, allowing the maintenance squad to execute standard internal objectives without immediate interruption. As barometric pressure plunges, personnel initiate standard lockdown procedures, securing all external equipment and verifying the integrity of the primary blast doors. The rapid deterioration of the local atmosphere triggers the automated navigational sensors, prematurely activating the primary visual beacon despite the daylight hours. Wind shear vectors begin to multiply exponentially, agitating the surrounding Celtic Sea and elevating the localized wave height to hazardous operational levels. Telemetry suggests the kinetic peak of the storm will impact the structure precisely at 2000 hours, perfectly synchronizing with total solar absence. Utilizing a brief lull in internal tasking, personnel ascend to the reinforced lantern room to visually verify the advancing marine hostility. Positioned near the absolute apex of the installation, observers note heavy kinetic swells beginning to breach the lower defensive boundaries of the tower. External audio sensors are overwhelmed by the immense atmospheric friction, masking the automated acoustic fog signal beneath a continuous roar of wind. The anticipated marine surge proves less structured than predicted, generating a chaotic, multi-directional wave pattern rather than uniform linear oceanic swells. Coinciding precisely with maximum tidal elevation, rogue waves aggressively strike the upper sectors, sending violent tremors down through the central granite column. The massive physical impacts generate low-frequency acoustic vibrations that resonate through the entire architecture, signaling potential external infrastructure degradation. Primary power generation fails repeatedly as localized wind shear directly impacts the exterior exhaust ports, effectively choking the diesel engines. The automated control matrix deliberately shuts down the combustion systems to prevent catastrophic mechanical failure from carbon back pressure. Surviving the nocturnal operational cycle now relies entirely on the structural integrity of the high-capacity battery reserves located in the lower decks. Under standard unmanned parameters, the diesel generators remain dormant, acting solely as a fail-safe when the primary solar array encounters sustained cloud cover. However, human occupation radically alters the energy consumption profile, introducing a constant thermal drain from the continuous operation of the internal boiler. This continuous domestic electrical draw mandates aggressive generator usage to maintain the battery banks at optimal defensive thresholds. Navigating the internal vertical axis during the storm peak reveals a distinct acoustic gradient, with lower levels offering marginal acoustic shielding. Despite the depth, high-frequency structural vibrations propagate downward from the damaged helipad, turning the primary granite column into a massive tuning fork. Operational personnel utilize the lowest accessible compartments to execute temporary psychological withdrawal from the extreme kinetic environment outside. Within the reinforced sleeping quarters, the structural mass of the lighthouse heavily dampens the exterior atmospheric violence, permitting necessary cognitive recovery cycles. The following morning reveals a stabilized barometric pressure and a systematic reduction in wind velocity, signaling the total passage of the Goretti anomaly. Post-storm external assessment protocols are immediately initiated to quantify infrastructural degradation and prioritize immediate manual repairs. The primary superstructure remains uncompromised, demonstrating the extreme efficacy of late 19th century maritime fortification engineering against modern hyperstorms. However, peripheral external assets sustained significant kinetic damage, specifically within the aerial deployment zone situated above the lantern room. A rogue vertical swell successfully displaced an entire section of the aluminum helipad grating, pushing it beyond its designed structural tolerance. This failure was a calculated architectural safeguard, utilizing specialized shear pins engineered to snap under extreme load to prevent transferring fatal stress to the main tower. Repair squads immediately deploy to the exterior perimeter, tethered to the main structure, to replace the compromised shear pins and secure the landing grid. Concurrent internal maintenance schedules continue uninterrupted, as secondary teams recalibrate atmospheric sensors disrupted by the extreme localized pressure variance. Maintaining optimal unit cohesion in these severely restricted operational environments requires strict adherence to scheduled caloric intake and communal recovery periods. The internal galley, operating under absolute minimum spatial tolerances, functions as the primary hub for unit morale and psychological stabilization. High-density nutritional preparation acts as a critical force multiplier, countering the physical exhaustion generated by sustained high-stress maintenance cycles. Surviving a 12-day isolated deployment necessitates a high degree of interpersonal adaptability, as the confined geometry amplifies standard psychological friction points. The specialized engineering cadre operates as a highly synchronized, albeit unorthodox, operational unit bound by the shared hazards of the maritime deployment. This specific operational rotation generated an excessive logistical burden, combining the standard biannual task load with rapid post-storm infrastructural triage. Documentation of these highly specialized procedures remains a secondary objective, strictly subordinated to the immediate physical requirements of the primary maintenance mandate. Upon the completion of the operational window, the extraction aircraft returns, severing the squad from the Lighthouse and re-establishing the logistical tether. Unlike standard civilian maritime operations, this specialized cadre does not enter a prolonged recovery phase upon extraction to the mainland. Personnel are immediately cycled back into the active roster, transitioning to localized depot maintenance or deployment to secondary coastal installations. The rigorous operational tempo guarantees that Trinity House maintains a constant state of readiness across its entire network of critical maritime assets. The dissemination of these operational recordings serves as a strategic recruitment tool designed to attract capable personnel to this highly demanding, low-visibility sector. Sustaining this critical infrastructure requires a unique psychological profile, combining advanced technical proficiency with an absolute tolerance for extreme physical isolation. The next scheduled tactical deployment shifts focus from the exposed Atlantic approaches to a confined operational theater within the Bristol Channel. Target coordinate, Lundy Island, a massive granite outcrop stretching precisely 3 miles in length and half a mile in width. This isolated landmass functions as a massive natural breakwater, significantly altering the local hydrodynamic flow and creating complex navigational hazards. The island's geography remains strictly uncompromised by modern infrastructure, preserving a highly active biological zone dominated by dense seabird colonies. Strategic control of this maritime choke point is maintained by 3 distinct lighthouse installations positioned along the high-elevation ridgelines. Currently, 2 of these structures remain fully active, projecting overlapping arcs of high-intensity light to guide high-tonnage shipping through the hazardous channel. The incoming maintenance squad will systematically audit both active installations, applying the same rigorous diagnostic protocols utilized at the Longships coordinate. Environmental conditions within the Bristol Channel dictate a highly compressed operational window, requiring maximum efficiency from the deployed engineering assets. Unlike the absolute vertical confinement of the rock pillar lighthouses, Lundy Island offers an expanded terrestrial perimeter for limited personnel maneuverability. The expanded footprint allows for the staging of heavier logistical assets and minimizes the immediate psychological pressure of total spatial restriction. Furthermore, the island sustains a minimal civilian presence, including a functional public house, introducing a stark contrast to standard isolated deployment protocols. This minor civilian overlap provides an irregular, yet highly effective, localized node for immediate psychological decompression between intense maintenance shifts. Preparing for the Lundy insertion requires a complete recalibration of tactical loadouts, shifting focus from vertical rope access to extended overland traverse equipment. The strategic objective remains absolute: guarantee the uninterrupted functionality of the United Kingdom's primary coastal defense and navigation grid. Every sheared pin replaced, every telemetry sensor calibrated, and every mechanical block cleared directly ensures the safe transit of global maritime trade. The operation exists entirely outside the public consciousness, a silent, continuous war against the relentless kinetic degradation of the ocean environment. The personnel executing these mandates accept the inherent hostility of the operational theater as the baseline parameter for their daily professional existence. Success is measured strictly by the absence of maritime disasters. Failure is mathematically calculated in tonnage lost and economic supply lines severed. The grid remains active. The next operational cycle begins immediately.